Why do we have only 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17, including this boy in the class? This is lecture number 6, right? So it's an exponential fall off. I can hope that by the lecture number 10 there will be one person in class. All right. So have you folks been following Piazza at all? You'll observe there are 2 categories of questions, 3. One is the usual person who's got some kind of minor confusion. The second is a category of really smart questions, good questions that I enjoy seeing, and very often you will find mistakes of what I say, and I like this. I mean, I get defensive, I can't help it, I'm human, but the fact is I like to, if people find mistakes with what's on the slides or what I say, I like to be informed of it, so that instead of making a fool of myself just infinite times all the way into the future, it stops in this class and I don't do it the next time. And then there's a third category of questions which basically tells me that this person hasn't watched the video, he hasn't seen the slides, or if they've seen the slides and watched the video, they've done it at 1.5x and jumped over various portions, so that they can finish a 1.5-hour lecture in 15 minutes. And then you get questions where it's very obvious that they've done that, right? So what I plan to do now, henceforth, is keep track of questions which are obviously from students who haven't bothered to actually follow the material. I can't penalize you for attendance because we don't have mandatory attendance. We cannot. I can't penalize you for not watching the lectures. So I'll be keeping track of this. And so henceforth, this is not for you guys, but anybody who posts questions whose answers are already on the slides and lectures in the videos, you might just lose points. And I haven't yet decided how much I'm going to be assigning to attendance points, but it's got to be sufficient that it actually worries you, right? Because the point of my coming here and doing these lectures is that you're supposed to be watching this stuff. And if you already know this stuff, you have no business being in this class, right? "30 people in lecture 7 is kind of not okay. All right. So where we had finished in the last class, before Mike's lecture, was we had just sort of seen how neural networks can be trained via gradient descent, and the gradient descent and the derivatives required for gradient descent can be computed using backpropagation, and that backprop based gradient descent. So again, the paper and the paper that talked about it and the manner in which I presented it, I said backpropagation is not guaranteed to find the correct solution even if it exists. So there's something wrong with this statement. What's wrong with that statement? No, it's much more mechanical. Backprop is not solving the problem. Backpropagation, what does it actually do? It calculates gradients. It calculates derivatives. Why does calculating derivatives have to do? What does it have to do with finding the optimal solution? It's what you use the derivatives for that matters, right? So the statement is fundamentally broken. It just happens to be what was the title of the paper, right? And we also saw But anyway, the point is gradient descent based methods might not find you the optimal solution, might not find the solution. What they're really trying to say, and what we were really trying to say, is that the local minimum that you find, that local minima in the objective function used to optimize the network. Remember, we built an objective function that was differentiable because classification error is not differentiable. That might not actually, the local minimum over there might not actually correspond to the answer that you want. And the reason for this was very simple. The reason for this was when you compute, when we design these objective functions, we are sort of designing an objective function which carries information about how far you are from how far the data instances are from the boundary. So for example, if I were using something like a sigmoid, if I have a couple of pluses over here and a minus over here, this kind of decision boundary versus, and say I have a bunch of minus here, I have two different decision boundaries over here. And if I'm using a sigmoid, and if I have any kind of limit on how steep the sigmoid can get, that means the fact that these guys are very close to the boundary means that these guys aren't actually giving you enough positive points to account for the fact that this guy is misclassified. This guy is correctly classified, right? This extra distance might actually make up for the misclassification error of the negative point. And this happens because you're actually taking into account how far the data instances are from the boundary. And the reason we need that is that's how you make the whole thing differentiable, right? And so that's one of the that's one reason. Even though you might be hitting the optimum of your objective function, it might not be the perfect answer, but we claim this was not a bug; it was a feature. That it keeps things from swinging around wildly. That you're trading off bias in favor of variance, right? So we assumed anyway that the training arrives at a local minimum. Thank you very much.
Yeah, sure. I think I lost like 10 cents or something.
That's okay. And a quarter. I got it, don't worry.
Okay, sure.
Thank you very much. Okay. If I happen to fall asleep while teaching, just wake me up. Okay. Now, what do I mean by saying does it always converge? What does it even mean to say does it converge? Remember, this is an iterative algorithm. It has to walk its way to the minimum. The question is, will it actually come to the minimum? Now, it might not. It might actually, you might be doing all the right things, but it might not come to the minimum. And we will see how this can happen. And so all of this, it's kind of hard to analyze these for an MLP because we saw the loss function of an MLP can be very complex. That was the last thing we finished with. There is one class of loss functions that we are very comfortable analyzing, namely quadratic functions, right? Now, there was a nice discussion on Piazza in the past couple of days, which I happened to actually catch on the plane, where people are asking, does the second derivative condition really, is it sufficient to find a minimum or a, if you say the derivative is 0, does the second derivative condition suffice to decide if something is a local minimum or a local maximum or not? And the answer is it doesn't, right? So why have we actually been inflicted with this theory all our lives that you must check the derivative and then you must check the second derivative? If the second derivative is positive, you're fine, it's a local minimum. That's not a sufficient condition. I mean, that's a sufficient condition. That's not a necessary condition, right? So in the sense that you can come up with functions where the second derivative may be 0, the fourth derivative may be 0, the nth derivative may be 0. You've got to keep looking further and further out. And so the second derivative by itself doesn't tell you anything. If I have a function of this kind, or this kind, or this kind, right? Out here, the first, second, third, fourth, fifth, sixth, and seventh derivatives might all be 0. Just by looking at these guys, you can't tell me if it's a minimum, a maximum, or a inflection point. So why were we speaking of second derivatives? Anytime we speak of second derivatives, we are doing something that is very common. We use the so-called streetlight effect. You might have heard of this joke, right? That some guy lost a coin in the bar, but he's searching for it where he can actually look. And that's exactly what we do. We have no idea how to analyze the functions in general, but we are pretty good at analyzing quadratics. So we're just going to come up with second order approximations to everything. And every statement we make generally tends to be in terms of the second order approximations. And when it comes to second order approximations, you can actually they form some sort of a best case scenario. And why are they a best case scenario? So think of comparing, let's say, x squared, well, this is a very bad x squared, versus magnitude of x versus, say, x raised to 4, and so on, right? So this is magnitude of x, this is x squared, this is x raised to 4. You can keep raising the orders. All of them have a local minimum at 0, right? The problem with the magnitude, of course, is that it doesn't matter how far away you are. The derivative doesn't tell you how far away you are. The derivative is a constant, and at the optimum, it's not differentiable. So that's an issue. This quadratic, it's beautiful. It doesn't look like what I've drawn. I'm really bad at drawing quadratics, but the derivative actually is a function of the distance from the minimum. That's a linear function of the distance. It carries information about how far away you are, and it continues to be non-zero all the way to the point, till significant, because it's a line, right? All the way to the optimum. The fourth order function has also got a minimum at 0. But what would happen? Out here, so let's say you were doing some kind of a gradient descent. This guy would nicely step and come out here. Because you continue to have significant derivatives almost until you actually hit 0, right? This guy is going to take giant steps here, but by the time it comes here, the derivative is so low, so weak, that it basically flattens out. Your standard algorithm will not be able to differentiate between this entire range of points based on the resolution that you're using, right? The steeper the function gets at the sides, the shallower it gets near the minimum. So in that sense, the quadratic is this beautiful, crossover point between something that can't really be that is analytically difficult to handle, and something that becomes too flat for you to actually get a reasonable handle on how it's going to behave. So, and which is why we talk about quadratics in pretty much everything that we do. Now, the loss functions that we assume, they are generally not convex. Now, a convex loss function is any function that's got sort of continuously curving upwards. All of these are convex loss functions. What do I mean by a convex function? If I have a function of this kind, if I take any 2 points on the curve, and if I connect them up with a line, then every point in the line is going to be above the curve. That's a convex function. It's a very simple definition. So over there, the curves on top, they are convex. The curve at the bottom, it's not convex, although it has a nice global minimum, right? We can also speak of convex sets. And there are many ways of actually mathematically characterizing convexity. They all mean the same thing. You can also speak of convex sets. If I have a set in some space, a set is convex if I take any 2 points and connect them up, and every point on the line that connects these 2 points also falls within the set. So the set on top, that's convex. If you take the contour plot of a convex function, all the contours, equal value contours, are going to be convex also. The set at the bottom, that's not convex, because If I travel in a straight line from x to y, at some point you have to leave the set. General analyses are going to assume convex functions over convex supports because these are convenient to analyze the searchlight effect. Now, what do I mean by convergence of gradient descent? Now, an iterative algorithm is said to converge to the solution if the value updates eventually arrive at a fixed point. Okay. And when I mean by fixed point, I mean the location where a point where the gradient is 0. And further updates do not change. Gradient-based updates do not change the estimate. So I have now your gradient descent method might not actually converge, even though the optimum exists. And we'll see why in a bit. Okay. So what could happen? You can have behavior like the one on top. You keep taking steps, and each point you're taking a step which is a function of the current gradient. And then the steps are going to get shorter and shorter as you get close to the optimum, and then you stop. That's a nice converging solution. Then in the second case, it does kind of get close to the optimum, but doesn't actually get to the optimum. It keeps bouncing around. And that's a jittering solution, right? That's not converging. And the third case, instead of actually going to the optimum, you begin taking steps that are too large and get out of it. You basically swing out. So that's a divergent solution. The kind of solution we want it to be converging, right? Now, what are the conditions for convergence? When will the function actually behave in this manner where the solution actually goes to the optimum point? Now, you can speak of a convergence rate, and the convergence rate basically is often defined in terms of this. There are many ways of defining convergence rate. It's basically the any numeric quantification of convergence of series can be used over here because there's really a series. You have a series of steps, right? It's a mathematical series. But so what you're really trying to see is if the series is converging, and one standard mechanism for quantifying the convergence of the series is how far away are you from the final endpoint of the series. Here in this case, the ideal point that you want to get to is the actual minimum, right? So if you are walking in this direction, if this is your minimum, at this point, this is the distance. At this point, after one step, this is the distance. This ratio tells you what fraction of the remaining distance you have covered. And that's one nice way of quantifying how fast you're currently converging. And if this ratio is constant or upper bounded, then the convergence is linear. Because what this means is that if it's not upper bounded, then the distance of the next point can be much greater than the distance of the current point, right? So obviously the sequence is blowing up. You want this ratio always to be less than 1. That's when you know that you're always sort of going closer and closer to the solution. Even if this ratio is occasionally greater than 1, so long as on average it's less than 1, you can expect that you're going to be going closer and closer to the solution, right? And so now, if I have a constant of this kind, and if the constant is lesser than 1, we will call it linear convergence. It's linear because what happens is the actual rate of arrival at the optimum is exponentially fast. So if you take k steps, then after k steps, you're going to be c raised to k closer to the optimum than you are at the beginning. But if you think of it in logs, you're going to get a k log c. So in the log domain, it's linear in k, so we call it linear. But it's actually, when I speak of linear convergence, the algorithm is converging to the optimum exponentially fast, right? Now, let's go to our favorite setup, quadratic surfaces. A quadratic surface is a nice board, right? If I think of a quadratic function of one variable, then we will typically write it as half ax squared plus bx plus c. The half is simply a matter of convenience, so that when you take the second derivative, it's a, okay? Yeah.
In the previous thing, how would you know x stands for like a neural network? You
You wouldn't. And we are just speaking of the rate of convergence. That's all, right? Of a property. For example, if I know x star, why do I even need to bother about going?
How can you measure the rate of to measure the rate of convergence? You need to know f of x star. Right?
You can get guarantees without knowing it. And one of the cases where you can have such a nice guarantee is for quadratic functions, right? So for quadratic functions, I can start off at some point, and the mechanism is what we saw. You're going to take a step in the direction against the gradient at each time, right? So I wish I had a laser pointer, but you're trying to minimize that quadratic function, half aw square plus bw plus c. The derivative, the second line on the slide, is mentioning the gradient update rule. The update, the k minus k plus 1th update is the kth update minus some step size times the derivative at the current location. Correct? Now, we're trying to estimate a scalar parameter w. Now, what is the step size that will get you to this optimum fastest? Can you look at this and tell me? That's to answer your question, right? Here, if I know the function, I don't need to know where it's minimum. I can tell you the step size where it will get there fastest for the quadratic. And how is that the case? I'll give you guys a couple of seconds to think about it, and then I'll actually tell you. Rohit, how would you decide? Yeah, and what? So what would the corresponding step size be, optimal step size be? The answer is right, but what would the step size be to make sure that you get there in a single step? So let's work it out, okay? Now, something is wrong. I'm not sure this was supposed to be. I keep editing this slide, and every time I edit the slide and save it, this figure changes because Microsoft messes up on me. So the figure to the left is supposed to be a bowl. So let's not get to the slide. Okay, I have, f of x equals half ax squared plus bx plus c. That's going to look like so, right? Now suppose I'm at some current point x0. My current estimate is x0. What is the Taylor series expansion of this function around x0? Everybody's familiar with what a Taylor series is, right? Who doesn't know what a Taylor series is? Anybody who doesn't know what a Taylor series is? So Lula, you can tell me, what would the Taylor series of expansion of this be around x0?
So it would be the original function.
Original function where? At x0.
The first derivative and then plus the second derivative.
What is the second derivative going to be? Okay, I'll just write this as f double prime x0 you forgot the half. Correct? Perfect. And do I need to expand it further here?
No.
Because there are only two. It's a second order function. The Taylor series approximation is second order, right? Now, how do I solve for the optimum over here? How would I solve for the optimum? I have given you the function.
Yes. Find the derivative, set it to 0.
Find the derivative and set it to 0. This is f prime x. So what is the derivative of this guy? This is going to be f prime x0, right? Plus 2 and 2 will cancel. F double prime x0 x minus x0. Is that correct? Yeah. So this equals 0. So what is x? X equals minus of f prime x0 by f double prime x0. That moves this over to the other side, divides by this guy, and plus x0. right? Make sense? We just sort of took a derivative and equated it to 0. Now, if I claim I'm going to use, now look at our gradient update rule. Our gradient update rule is going to be x1 equals x1 equals x0 minus eta times f prime at x0, correct? Compare the two. What step size will give me, get me to the optimum in a single step? Pardon me?
1 by the second derivative.
So implies eta opt equals 1 over f double prime x0, right? If I use that step size in a single step, you're going to get to that. No, I'm not scaring you, sorry. And I can do that without knowing what the optimum is. Okay. So more generally, regardless of what the step size is, if my step size is appropriate, then for a quadratic function, the convergence is linear. This can be easily shown. Okay. So here, the figure to the left, this is the, thank you, Microsoft. Just imagine there's a bowl and it's showing all the beautiful necessary parts. This is basically what we found. I've written E as my function out there, but basically what you find is that the optimal step size is the inverse of the second derivative of the function. But what is the second derivative of this guy? Anywhere. What's the first derivative? The first derivative is simply going to be ax plus b, correct? What is the second derivative? A. The second derivative doesn't depend on the location, right? Which means that you actually can get to the solution in a single step from any current location. The second derivative is simply going to be A inverse. Yeah? So you see how this works. For a quadratic, it's trivial. Now, what would happen, just keep this in mind. Observe that. Now, so I have a bowl, right? I start off over here. I'm going to use this rule, xk plus 1 equals xk minus eta times f prime of x. This is my gradient descent rule, okay? So case 1, eta equals, and my function is whatever, it's quadratic, okay? The eta is f double prime xk inverse. If I do this, where would the next, and say this is my current estimate. This is f of x. X, I'm here. If I use this inverse of the second derivative of as my step size, where will the next estimate be? Pardon me?
What is the function again?
It's just a quadratic.
Oh, it's a quadratic.
Just a quadratic, right? So yeah, add the minimum, okay? That's going to get me over here. Suppose eta is less than f double prime xk inverse. Remember, this is a constant, right? So this is A inverse. F of x is half ax squared plus bx plus c. So what would happen if the step size is less than the optimal step size? Where would the next step be?
On the left of minimum.
On the left in this particular case, it's going to be here, but obviously I'm not getting to the correct solution. So the next one's going to be here, the next one's going to be here. It's going to converge squeakily to the solution, correct? Make sense? What if eta is greater than f double prime xk inverse? What would happen?
It will always overshoot
Okay. Now here is this. Do you observe that there are two conditions over here? So initially, let's say my eta is just slightly greater than the optimal step size. What would happen? This is going to go here, right? And then instead of coming here, it's going to go here. Then instead of coming here, it's going to go here. It's going to oscillate. Is there an eta where the thing is going to blow up?
Greater than 2.
Because so for eta equals 2 times f double prime of x inverse, this is going to go straight to this location, correct? Twice the step. Remember, it's a quadratic, it's a symmetric bowl. If some step gets you to the optimum, the same step is going to get you back to the same height on the other side because it's a quadratic, right? And so it's going to keep bouncing back and forth and back and forth. What if eta is greater than 2f double prime x k inverse? This is actually going to converge or diverge. It's going to blow up. Right? Make sense to everybody? Yeah. So this is basically what is happening over here. That's there on the slide. You see just a pictorial characterization of what would happen in this particular case. Okay. Now, this is for quadratic functions. What about for a generic differentiable function? I give you a function. Remember, we are always talking about it in terms of quadratics, but suppose I give you some random function, except that I tell you this function has at least 2 derivatives everywhere. Then could we use the same behavior to characterize convergence of gradient descent for this function? You gave me an answer, partial answer some time ago without knowing it.
Yes.
How?
Not sure.
Okay, anybody want to take a guess? Taylor series, right? Second order approximation. I can take pretty much if I have some crazy function. If I have some crazy function, this is convex, but it's not really quadratic. I can take the current location, get a second order Taylor series approximation at that point, which will be a quadratic, right? And I could look at that quadratic function to get an idea of what a reasonable step size might be, right? And so if I was just taking a second or any arbitrary function, I can take a second order Taylor series expansion, truncate it after 2 components, two terms, 3 terms, including the 0th order term. And then the optimum step size, I can assume, is going to be the inverse of the second derivative of the function at the current point. And you can also assume that if you're more than twice, if the step size is more than twice this value, you're going to blow up. Everybody with me? Okay. Now, what if you have multivariate inputs? So this is for a nice scalar, right? It's a scalar function of a scalar variable. But now I give you a multivariate function. So the lady in the corner, how would you characterize a quadratic of 2 variables? Someone else? What would a quadratic of 2 variables be look like? It's a bowl, I know. Of course it's a bowl. But what exactly is happening when I say it's a bowl?
You have single minima.
Yeah, but functionally, what is the functional form for it? It is a single minimum, of course, right? What's the functional form for it? Can you take a guess? You're there. What's your name? Yeah, I can't hear you. Huh? Michaela. Okay. So how would you actually characterize mathematically characterize a second order quadratic of say two variables? So write the functional form for it. Let me do it. Somebody else want to take a guess? Okay, thank you. Okay, say that aloud. Ax1 squared plus bx2 squared plus cx1 dx2 plus e, right? There's some term missing. Plus fx1 x2, right? The combination of the total number of terms that are combined in any term term is going to be upper bounded by a quadratic. I can write this in vector form. In vector form, I can put x1, x2 in a vector, and then my quadratic is going to be half x transpose ax plus b transpose x plus c. That's going to be my quadratic. It's the same equation, right? Any number of variables. And now something interesting over here. What does this actually decompose to? Now let's consider a very special case. I have two variables x1 and x2. So the first variable has a quadratic half a1 x1 squared plus b1 x plus c1. The second quadratic has the form half a2 x2 squared plus b2 x2 plus c2. So I've just written quadratics for each of these guys. Now for any value of x1, x2, regardless of x2, this guy is going to have the same shape, correct? What would happen as x2 changes? The height of that function bowl is going to change. That's all that changes, right? Depending on the value of x2, the height of the bowl is going to change. Similarly, for any value of x1, this guy is going to have the same shape. What would happen as x1 changes? The height of the bowl is going to change, right? So overall, what do you think this joint function is going to look like? It's going to look like a bowl, right? But how would the bowl be aligned? It's going to be axis aligned. So here's what your function is actually going to look like. If I think, so that's your standard quadratic function, E, multivariate. And this is a special case where the matrix A is diagonal. If the matrix A is diagonal, I can simply write it as a sum of many different quadratics, right? It's you have uncoupled each one of the directions. And we're going to get into, what is this business of a Hessian in a bit. But if I now plot the overall function, and if I look at it from the top, this is what it's going to look like, right? This is a bowl. Those are all equal value contours. As it gets bluer, it gets deeper. I'm assuming that it's convex in every direction. And so it's going to look like a bowl which is wide in one, the widths in different directions are going to be different. Okay. And if you actually slice it, basically, if I take any vertical slice, they're all going to have the same shape. The heights will be different. Any horizontal slice will all have the same shape. The heights are going to be different. Now, suppose I use a gradient descent rule. And let's say this is one bowl, and this is the other bowl, right? What is the optimal step size for this guy at any point? Speak up, yeah? A1 inverse, right? The optimal step size is going to take A1 inverse. So over here, this is going to be A2 inverse. What is the gradient descent rule, the vector format, when we are using the gradient descent rule for something like this? The gradient descent rule is going to be xk plus 1 equals xk minus eta times the gradient with respect to x f of computed at xk. Right? So the step size, the eta, is the same for every single direction. See what I mean? You're taking a step against the direction of steepest ascent of the function. But then if you consider, so what can you tell me about what would be a good step size?
It's different along different directions.
The optimal step size is different for different directions, right? So what would happen if I took A2 as my step size? A2 inverse as my step size. Huh? What would happen? I'd get to the optimum along x2 in one step, but what would happen along x1? It's going to diverge, it's going to blow up, right? What would happen if I took A1 inverse as my optimal step size? It's going to get to the optimum point in x2, in x1 in one step, and x2 is going to take forever. It's going to become very slow, right? So what is the optimal step size? What is the minimum criterion you can impose for a step size in this condition, in this situation? That it must be smaller than the smallest optimal step size, or twice the smallest optimal step size, right? If it's larger than twice the smallest optimal step size in at least one direction, it's going to blow up, right? So what will happen here is the descents in this case are uncoupled. The optimal step sizes are different in the two directions. The optimum step size for each because the optimum for each coordinate is not affected by the other coordinates. In every coordinate, the optimum value is exactly the same, right? And so when you use a vector update rule of this kind, basically in every direction, you're using the same step size when you're using the vector update rule. And this direction that you're walking in is at 90 degrees to the equal value contour. Remember, the gradient is always orthogonal to the normal to the equal value contour, right? And so the problem with this rule is, here's what will happen. And let's skip that slide. I have this example. I have a quadratic in two variables where the two variables are uncoupled. So the optimum step size for the first coordinate is 1, for the second coordinate is 0.33. So which of these two represents the steeper bowl? Can you tell me just by looking at eta? You want the steeper bowl to have the smaller step size, right? So I would think the narrower side corresponds to eta equals 0.33. You would expect the wider one to correspond to eta equals 1, or eta opt equals 1, right? Now in the first case, I have used a step size where global step size where the step size is 2.1 times 0.33. So it's like 0.66 plus 0.06, 0.7 something, okay? What happens? 0.7 something is less than the optimal step size in the first coordinate. So it's sort of linearly converging to the solution along the first direction. In the second direction, it's blowing up, right? In the second case, the optimal step size is exactly twice the optimal step size for eta 2. What happens? In the second direction, it's going to oscillate. It's going to exactly oscillate. It's still converging linearly for the first direction. In the second direction, it's bouncing around, and it will bounce around forever at the same 2 points, right? Third case, it's 1.5 times the optimal step size for eta 2. Now it will converge, but it will keep jumping across the optimum. In the first direction, it's still kind of converging linearly, right? Fourth case, it's exactly the optimum step size for the second coordinate. So observe what happens. In one step, it has gotten to the optimum point for x2, but then x1 is getting there incredibly slowly, right? And if you try to keep it below the optimum step size in both cases, then it's going to slowly converge to the solution. It's going to take a very long time, right? So the step size matters. And if you have something that's between, the optimum step size and twice the optimum step size in every direction, you're going to get behavior of this kind. So convergence behaviors, now this is only with 2 dimensions. If I give you many, many dimensions, 700 dimensions, 70,000 dimensions, 7 million dimensions, it's really hard for you to know what's going on, right? And the behaviors become increasingly unpredictable as the dimensions increase. For the fastest convergence, ideally the learning rate must be close to both the largest optimal rate, step size, and the smallest optimal step size, because the closer you are to the optimal step size, the faster you're going to get to the solution. So if the ratio of this largest optimal step size and the smallest optimal step size is very large, the function is going to take forever to converge, right? This is what we'll call the condition number. If the condition number is small, the function will not converge. Now, what's the reason for this problem? First, I have 2 figures over here. You have many more slides that I'm not going to show. What's the difference between those 2 figures? Without looking at the slide. If I just gave you half, x transpose AX plus BX plus C, B transpose X plus C as my equation, by looking at those 2 figures, what can you tell me about A?
It's not diagonal in the second.
In the second case, the A is not diagonal, the space has been rotated, correct? So what is the Hessian of this function? What's the Hessian of this function? It's just the second derivative, right? What would it be?
It will be non-zero and the non-diagonal.
Look at this thing. What is the Hessian of this function? It's just the matrix A, right? And now here's the point. Regardless of how you give me this matrix, I can write a version of this function where the A matrix is symmetric, simply because I can transpose the whole thing and add the 2, and I get a symmetric A matrix. Okay? So in other words, this equation has always got a symmetric A. The Hessian is always going to be symmetric, number 1. Number 2, what are the eigenvectors of this Hessian? Look at the figure and tell me. Pardon me? The eigenvectors. So if this is like so, these will be the eigenvectors. The eigenvectors are going to be the directions of the principal axes of the bowl. And what is special about the eigenvectors? You can restate the entire equation in terms of variation in terms of this new coordinate system, which is the eigenvectors of the Hessian. And if you do that, what happens? The directions become uncoupled. Which is why when we are talking about optimizing higher order functions, we are speaking of Hessians. First, you're sort of saying, okay, I'm going to take the second order approximation, I'm going to rotate it, I'm going to talk about what happens along these directions, and now I can treat the directions independently. I can say that in this direction it's convex, in this direction it's concave, and other things like that, right? So the Hessian, the eigenvectors of the Hessian are just the principal directions of the bowl. Okay, so far so good. But now, why were we actually having problems where the thing could blow up? The reason for this is that the eccentricities in the 2 directions are different, right? The bowl is shallow in one direction, it's steep in the other direction. How can you fix this? Anyone? Alex? How would you fix that?
You can try to reshape the function.
Exactly. You can try to reshape the function. I can stretch the page along the x-axis, right? What I would like to do is to transform the space in this manner so that now it has equal eccentricity in every direction. And if I do that, now the optimal step size in every single direction is going to be the same. Right? So what I will do is to transform my space. I'm working with W. I'm going to rewrite the equation in terms of a W hat, where W hat has the form some S times W. Okay? Such that when I write the equation in terms of W hat, I get this beautiful quadratic, which is where the cross section is perfectly circular. A is an identity matrix, right? When A is an identity matrix, what's the optimal step size? It's always going to be 1. Right? So given this, just compare this equation. So let's just compare this, right? You don't even need to go in through the math, right? Let's just compare X transpose AX plus B transpose X plus C. Okay, I'm writing X over here. I meant W, but you get the idea, right? And the second one is half X hat transpose X hat plus some B hat transpose X hat plus C. Okay? Given this, and I'm telling you the two equations are the same, what is the relationship between X hat and X? Just by looking at it, you can tell me X transpose AX equals X hat transpose X hat, right? You don't even have to think very hard. Implies X hat equals what? A raised to 0.5 X. Right? Asymmetric. I can just write it. I don't even have to think very hard. And so what you mean, so what we are really doing is we are sort of stretching the space. We're transforming by the space by the square root of the multiplier for the quadratic term. Okay? And I'll skip that for the diagonal case. So now, if I just do that, now here's the magic. If I use that, it doesn't matter whether my original ellipses are axis aligned or not. Regardless of the shape of the original function, whether the ellipses are perfectly aligned with the axis or whether they're at an angle, when I'm done transforming things in this manner, the contours are going to be perfectly circular, right, or perfectly spherical. And once I do that, I can write my update rule in terms of the modified variable in terms of W hat. And now I can translate it back. And here I know that this eta, the optimal step size is going to be 1. No issues about it. Correct? We know this. And then I can modify that. And I can translate back from there to this guy into the original space. And it's simply going to come back with a simple update equation. I won't derive it. It'll take too much time. It takes 1 minute of derivation, but I think I'm being too slow today. It's WK plus 1 equals WK minus some eta times A inverse times the current gradient. Okay? And the optimal eta again is 1. Yeah? Now, if I have a generic differentiable function, this is for a quadratic, right? So for a quadratic, I've got this guy. For a quadratic, I've got WK plus 1 equals WK minus, you don't even need the eta. It's going to be A inverse gradient with respect to W of. Suppose I have a generic differentiable function. It's differentiable everywhere. It's twice differentiable everywhere, but it's not quadratic. What would a corresponding approximation be? What would you do? Anyone? What would you do in this case? Exactly what we did for the scalar case, right? And what did we do there? When I had a non-quadratic function, what did we do? Pardon me? We took the second order Taylor series approximation, correct? And then we took in terms from the second order Taylor series approximation. How will the multivariate case differ? It shouldn't differ. It's exactly the same thing. I can still take the second order approximation. And the second order approximation is going to now look like so. The value of the function at xk plus the gradient times, the derivative times, w minus wk plus half of w minus wk times the Hessian times the, this should be a transpose. Basically, this is just the Taylor series approximation for multivariate functions. If you had higher order terms, you're going to invoke tensors, but we're going to stop at the second order. Okay? Using this guy, what would the update rule now be? Anyone? If I use this, what would the update rule be? You want to tell me? If I use the second order approximation, what would the update rule be? Just equate it to the quadratic. I'll wait. I have half an hour. I'm going to wait for you to answer me, and the rest of the class will. Pardon me? So I want you to tell me what the corresponding for equivalent for this update rule is going to be. I can see you telling me the answer. Go ahead, finish it.
We can just plug it in.
Plug what in? What will?
The Taylor series.
If you plug in the Taylor series, what will that rule be?
There's no eta.
Yeah, there's no eta, but still, that's what the function there is quadratic, right? So what is this going to be? Anybody else want to take a shot, Alex?
Yeah, I mean, just subtract the inverse of the Hessian.
That's it, right? The A, the equivalent of the A is the Hessian when you're doing the quadratic, right? And so for this guy, it's simply going to be wk plus 1 equals wk minus now the Hessian at wk inverse, and yeah, the gradient with w at wk. Now, it's the same function. Nothing really changed. I just took one quadratic. It's a different quadratic. Instead of A, you had the Hessian, right? This is Newton's rule. This is exactly what Newton's rule is, right? So for generic differential multivariate convex functions, the update rule is simply going to say current step minus the inverse of the Hessian times the current gradient. That's the optimum, right? The eta itself ideally is 1, but in more generically, it won't be. So your more generic convex function is going to look like this. You have some function with some funny equal value contours. At the current location, you're going to make a quadratic approximation. In one step, you will find the optimum of that approximation. At that point, now you're going to make a second quadratic approximation. In one step, you find the optimum of that. And so on until you get the correct solution. The problem with this approach, now this is a beautiful approach. It's going to be very, very fast. The problem with this approach, if you have a complex model like a neural network with 5 million parameters, how large would the Hessian matrix be? Someone? N squared, right? It's going to be 10 raised to 12. You're not going to be computing the Hessian matrix, leave alone the inverse of the Hessian matrix. That's not going to happen. So and there's a second issue. I have a function like this. This function actually has a nice, it's like that, it's that kind of shape. So to give you a one-dimensional equivalent, say I have a function which looks like this. So we found that when you have a function that looks like this, and it's not quadratic, I can make a quadratic approximation, go here, then make a quadratic approximation, go here, and eventually you're going to find the minimum, right? But how about a function like this? This function has a nice unique minimum. But if I look at a quadratic approximation at this location, is it going to be convex? No, the quadratic approximation is that guy. If you find the minimum, there's no minimum of it. The minimum is wherever you want it to be, up at minus infinity or at plus infinity, right? There is no. So when you begin making quadratic approximations of these functions, you pick some location, you might actually end up going in the wrong direction. So you can't just use this method blindly, because the function, even though it's actually in some sense well behaved and it has a unique minimum, your second order method can take you to the wrong places and just blow up in your face, right? So what is a characteristic of a Hessian function that's going to take you to a bad place? It's not going to be negative definite or positive definite, right? And there are a great many methods which try to deal with this problem. First, they deal with this in two ways. A, they try to estimate the Hessian in a proper way, estimate it in a computationally tractable way. And secondly, they try to somehow modify it so that it's positive definite, so that you can keep continuing the algorithm regardless of the shape of the function. So these are things like the BFGS, Borden-Fletcher, Goldfarb-Shano, or the low memory version of it, LBG, BFGS. You might have encountered these terms. What are they really doing? They're all just trying to, various ways of trying to approximate the Hessian, or the Levenberg-Marquardt, where they estimate Hessians from Jacobians. And then you diagonal load these things to make sure that the eigenvalues are positive, various things. But for neural networks, we don't use it simply because the whole thing is going to be tremendously inefficient. But then there's a second issue. We were trying to make sure that the learning rate actually gets you to the optimum, right? Is this really necessary? Now consider a function of this kind. Let's say your initial point is out there where the arrows begin. Do you really want to go to a local minimum? Not really, right? Initially, you want to bounce around and go out of the local minimum. If that's a unique quadratic, if your step size is too large, you're still guaranteed that you're going to stay within the bowl. But if it's not a quadratic, and if you have all these ugly local minima, then the step size is going to make sure that you go out of any local minima and begin wandering the space at large. So what you really want is that you don't want to have the step size. This characteristic, eta greater than 2 eta opt, will help you escape local minima, but you don't want it to remain greater than 2 eta opt all the time, because then you're never going to arrive anywhere. It will never converge. So the solution is start off with a large eta, more than twice the eta opt, and then shrink it. Keep making it smaller and smaller. And if you keep making it smaller and smaller, eventually, at some point, the eta is going to be small enough that it's going to be less than twice the eta opt of the current bowl. We asking a question? Yeah. Right. At some point, it's going to, and then you're going to end up in a sufficiently large bowl, and then when you get to the bottom of that bowl, that's almost certainly going to be a local minimum. And in fact, if you shrink the eta opt, slowly enough, there are some guarantees. Yeah. More than twice.
More than twice. Was the goal of escaping? How is that different from just taking a random point and then starting over the gradient descent? It's like if the only goal is to escape, why we are not just taking a random point somewhere?
How many times are you going to do it?
I don't know, as many times as we do this step.
So the point is you can keep picking random points. You will never know where you are. So this is a more formal way of what we are doing is shrinking the step size at each time, and as you go through, the step size keeps decreasing. So eventually, you're going to begin converging. Okay, so that would not happen if you're just picking random points. You need some tests to know whether you're in a bowl or not, which don't really exist. Right? Yeah. Is right?
Is it possible that you can get stuck in a local minimum which is worse than the local minimum you started at?
It's possible, but unlikely. In statistical terms, it's unlikely. You can keep bouncing around, and eventually, just by chance, you get to a small enough eta opt. Eta, where you're in some tiny little, crater, and this will happen. It's not that it won't happen, right? But very infrequent. So how exactly do you decay the step size? There are various kinds of step sizes that have been proposed in the literature. But here is one step. Here is a standard technique the standard criteria that have some provable properties. A, you want the summation of your step sizes to be infinity, but you want the summation of the squares of your step sizes to be less than some constant, finite. What is it? Why do we need these two criteria? If your step sizes do not sum to infinity, if your derivatives are bounded, then it means that wherever the starting point is, I can draw a radius, and I'm guaranteed that I'm not going to be searching outside that radius, right? So which means I won't actually be searching the entire space for a global optimum. In order for me to be able to scan the entire space for a global optimum, I want this property to be satisfied. Because if it's not, think about it. If my derivative is, say, upper bounded by 10, and if the sum of the etas becomes 1 million, then the farthest I'm going to get from the current location is 10 million, right? If the optimum is a 10 million plus epsilon, I'm never going to find it. So you want the sum of the etas to be infinite. On the other hand, you want the etas to shrink. So the sum of one way to say it is the sum of the squared etas must be finite, right? Can you give me a function which has this property? Some function of k which has this property. Anyone? 1 over k, right? The integral of 1 over k is infinite. The integral of 1 over k squared is very, very finite. So typically what you will find is that most training algorithms, you're going to start off with a large eta, continue with it maybe for some time, then shrink it, and the overall property is going to satisfy both these conditions. Okay. Now, so gradient descent can miss obvious answers, and various convergence issues abound. The loss surface may have saddle points, vanilla gradient descent won't converge, etc., right? So, and the optimal learning rate for one component may not be maybe too high or too low for others. Second order methods normalize the variation across the different components to mitigate the problem of different optimal learning rates for different components. But this requires computation of the inverses of second order derivative matrices, which is not feasible and may not even be stable. Yeah? And the learning rate, the divergence causing learning rates may not be a bad thing for ugly loss functions, but decaying learning rates provide a good compromise between escaping poor local minima and convergence. Now, and many of the convergence issues that we find is because we force the same learning rate on every component of every parameter of the network. So let's take a step back. Can we, instead of having something of this kind, can I just have different step sizes for different parameters? The problem with this is this. A, you have to keep track of so many different parameters, right? B, even in the case of a quadratic, let's say I have a quadratic that's at an angle like this, right? And I have and I maintain different step sizes in different directions. Taking a step along this direction actually affects the value of the function in the other direction. So when I begin locally optimizing each of the setting the step sizes for the various directions, they will begin conflicting. So convergence cannot be, you might not converge. Bad things can happen. You first take a step along x and say, I've done something better. Then you take a step along y and say, I've gotten to a better place. But the step along y destroyed what you did along x, right? So you can't just ignore all of these guys. Nevertheless, various algorithms have been sort of proposed which try to use the derivative information for trends, but they don't actually use them absolutely. The problem with this, having derivative-based independent steps in each direction, is that they can begin conflicting with each other, right? So on the other hand, the derivative does tell you which direction you must move in to get to a better solution. So you have algorithms which sort of retain this information but throw away the value of the derivative itself. The two most popular ones are RProp and QuickProp. They are trivial to implement, amazingly effective. They've been around for 30 years. and I'm surprised people don't use them frequently enough. I'm not actually going to cover RProp. I was originally going to, but because we are kind of short of time, I'm going to just give you the usual caveat that I suggest you actually study up RProp and QuickProp, because we will have a nice little problem in the quiz which makes sure that you have understood what you're doing, what RProp does. I'll spare you QuickProp, okay? Now, but this RProp and QuickProp methods that decouple the dimensions can improve convergence. Now let's take a closer look at the convergence problem. With dimension-independent learning rates, the solution will converge in some directions but oscillate in others. So here is a very common solution, something that actually works, and in some case provably so, at least for the case of quadratics. Instead of trying to do dimension-independent learning rates for every dimension and just doing gradient descent, which we said can actually end up with bad behavior, you keep track of the oscillations. You emphasize steps in the directions that converge slowly. You shrink the steps in the directions that converge fast. So to give you an idea, these are the so-called momentum methods. And the most common way of doing it is that you maintain a running average of all the past steps. So for example, the dark red line shows you the actual sequence of steps. So what would happen is, if let's say you keep a running average of everything that you've done so far. If the behavior is like that, then keeping track of everything that has happened so far, you will realize that in the x direction, you are swinging around, but in the y direction, you're progressing slowly, right? So the simple thing is, okay, let me reduce the step size in the x direction so that I reduce the swinging around in the x direction. In the y direction, I'm smooth. Let me increase the step size in the y direction, right? Simple logic. And so you basically, and this you can do by just maintaining a running average. If I maintain a running average of all of the previous steps, if I'm bouncing around in the x direction, the average is going to the positive and the negative steps will cancel out. If I'm consistent in the y direction, they're always positive, they will add up. And so in directions in which the convergence is smooth, the average will have a large value. In the directions in which the convergence is not smooth, the average will cancel out. And you can use this behavior to decide what the step size must be in each direction. So here's the basic momentum update rule. The momentum update rule maintains a running average of all gradients until the current step. So let's say you have your standard gradient descent that's going to have behavior like the one to the left, where the direction in which you move is always orthogonal to the equal value contour. But then the one to the right, what you would do is this. You are going to, at each time, the step size is going to be some linear combination of the step size in the previous step and the current gradient. So you're going against the current gradient, but you're not depending entirely on the gradient. You're averaging this with the previous step size. You're maintaining a running average. Maintaining the running average is the same as computing a global average. We know that, right? And so what will happen over here is that as a result, you're going to be canceling out oscillations in some directions, enhancing oscillations and enhancing the step size in other directions. And then finally, this updated step is what you're going to use. Correction is what you're going to use to update your parameter value. Right? Very simple. It's a trivial thing. It has some very nice properties. Some of them are provable under conditions, right? And it is going to get you to the solution much faster. So how does that change your overall algorithm? That's training with gradient descent. What you would be doing is that you'd be computing the gradients, keeping an average of the gradient, and just doing subtracting some step size times the gradient, right? With momentum, things change. All you have to do is now you keep track of the step size. So at each time you compute the derivative, the first thing you do, the change in code is minimal. The first thing you do is to compute a running average of the current derivative and the previous step size, and that's what you're going to add to the current estimate to get the next estimate. So the momentum method, the way you do it, at each time you compute the current step, right? So let's say you are in the new location. Let's say you're in the first dot. You made a move. You got into the second dot. Then at that dot you would compute the gradient, which might be like so, right? But then you don't actually just keep that gradient. You take that some scaled version of the gradient plus some scaled version of the previous step, and that is going to give you your resultant step. So now you're going to repeat the same process. Over here, having come here now, at this point, the horizontal line, near horizontal line is going to be a current step. You'd compute a gradient, which is probably going to be orthogonal to it. So the average of the two is going to go slightly upwards, and that's where you would move, right? So what is happening is you're computing the gradient, then adding the average, the past step to get to the next step. So it takes a step along the past running average. So what it's doing is, observe what is happening over here. The actual step has two components to it. You can break it down into two steps. The black line is actually two steps. First you take a step in the blue direction, then you take a step in the reduced red direction, and that's going to give you a net update, right? So first you move along the gradient, then you move along a scaled version of the previous step, and that's going to get you to the current estimate. It turns out that if you change this order, things get much better. You just reverse the order of operations. So what would you do over here? This is Nesterov's accelerated gradient. It's a brilliant paper, and I don't remember exactly which paper this was, one of Nesterov's paper. The paper starts off with obviously, and it makes a statement, and then has a page and a half of math afterwards which says QED. It took me 2 days to understand why that obvious thing was obvious. That is the first line in the paper, right? But anyway, so that's an issue with mathematicians, particularly Russian mathematicians. Stuff that's obvious to them may not be obvious to you. But here's how it happens. So let's say this is the current step, right? Now instead of computing the gradient at the current location, you just take a step forward, which is a reduced version of the current step. Then compute the gradient, and that is going to give you a resultant step. And that is going to be the final update, right? So Nesterov's method is like so. You're going to, the current step, the next step is some beta times the current step, right? Because you're actually taking a step in this, extending the current direction, plus or minus some eta times the gradient computed at a location where you arrived after having taken the current step. Yeah? And then you make the correction exactly as before. So comparison, this is a very nice comparison of the two by Hinton. So you can see what happens with Nesterov's method versus the gradient descent method, with the momentum method. The momentum we already saw was better than simple gradient descent, right? The blue line is what happens with momentum. Let's say you've taken an initial black step, then you're going to compute the gradient over there, which is the short blue line. Then you're going to add a scaled version of the previous step, and then you would end up on that line out there going up. And if you keep extending it, it's going to take several steps to get to the optimum. In Nesterov's method, you extend the black line first, then compute the gradient, and then take the final green step. And you can see it's getting to the optimum much faster. So Nesterov has this nice proof which shows that this is really the optimal thing to be doing. So training with Nesterov's method, because of this peculiar operation where you first take a step, extend the current step, and then compute the gradient to obtain the final current step, the arithmetic changes a little bit. So as before you'd compute, what you would do is to actually first take a step. So you're going to go from wk, you say wk equals wk plus beta times the step, right? And then you compute the gradient at that point, and then take a step back against the gradient, and then compute the updated, and then you find out what the real modification was, right? So momentum and trend-based methods, we're going to return to this soon. The story so far, we've been talking about convergence. Vanilla gradient descent may be too slow. Gradient descent can miss obvious answers. We already saw that. This may be a good thing. Vanilla gradient descent may be too slow or unstable due to differences between the dimensions. Second-order methods can normalize the variation across dimensions but are complex. Adaptive or decaying learning rates can improve convergence. And methods that decouple the dimensions, like RProp and QuickProp, can improve convergence. Momentum methods which emphasize directions of steady improvement are demonstrably superior to other methods. Coming up in the next class, actually, I'm going to be covering some of this on Friday in a recorded lecture simply because I missed the previous one. The final lecture on training will be next Monday. By the way, I hope you attended Mike Tarr's lecture. If you haven't, please look at his video. Mike Tarr is one of the best person in the field in what he does. Also, he's very open to doing projects, and if you actually work with him, he has some very interesting ideas, very fundamental stuff on computational modeling of the workings of the brain. So reach out to him, and I'm sure he'd be very happy to actually work with you guys. And you have high odds of a high quality publication in a somewhat orthogonal direction, right? Everybody is publishing in ICLR or ICML, but that's going to give you exposure to a different way of thinking, which could be very interesting. Questions? No? Thank you. And in the next class, I hope to see a few more people in the class. This is really sad.